So good evening, everyone, and welcome to today's live session. We are into the week 10 live session for the course NOC25 me57 Nonlinear Vibration. This course is being taught by Professor S.K. Dwivedi, IIT Guwahati, and I'm Rashi Aditi Ranjan, NPTEL PMRFTA in the Department of Mechanical Engineering, IIT Patna. So we are already done with the 9 live sessions up till now, and we are almost towards concluding the course. After today, there will be only 2 live sessions and one more extra session of 1 hour, which I'll be taking. And okay, so in this live session, I'll be discussing some questions in which we will revisit what has been taught in this week's lectures. And then we will also solve questions which will be helpful for solving your assignment problems. Okay. So coming on to the overview of what has been taught. So, this week's sessions were mostly roaming around about vibration, absorption, and reduction. Okay. The question is, why do we have to think about vibration reduction? Why is it even needed? So, when we talk about any machine that is operating, or if we have a sensor which is placed on a machine, in that case, if a machine is in a dynamic condition, it may happen that it encounter some kind of a vibration. Okay, like for example, if you take a washing machine, and you must have observed that when the washing machine is working, it has some kind of a vibration that is there. Okay, if you look into the like the old washing machines, which were not automatic, it had two chambers, one for washing the clothes and the other one was drying the clothes. So it used to happen that in the drying chamber, if you do not properly place the wet clothes, there will be very high vibration, okay, because of the rotation, and it actually creates sound, and it also transmits from the ground to the other machine, or it may get transmitted to some sensor which is already placed on the machine. Okay. So in order to, think about the efficiency of the system, and then we have to think about the condition in which the machine is operating. Okay. So if I talk about efficiency of the system, if my machine is producing some extra vibration, okay, then what is going to happen? Because of that extra vibration, some extra energy is getting out of the system. In what form? In the form of vibration. Okay, but the machine is not designed to give that vibration. That is an extra energy which is getting out of the system because of that vibration, right? So it is essential that we somehow try to reduce the vibration. Okay, then we talk about if a machine is operating and it is producing high amount of vibration, and then I am standing beside the machine. So, I'll also feel that vibration through my legs, right? I'll also feel the vibration. That way, if some other machine is kept beside that machine is also going to feel the vibration. Because of that vibration, it may happen that that machine is going to encounter more vibration, maybe because of the resonance condition, right? So, in that case, it is important that the vibration is isolated. We isolate it, right? So, I hope that you understand that what is the need of vibration reduction. Vibration reduction is mostly very important in any kind of a dynamic machinery, right? If any machine is working in a dynamic condition, the vibration reduction techniques are usually used. Okay, and then there are different types of vibration reduction techniques, which is essentially mainly two types. One is for vibration isolation, and the other one is for vibration absorption, which we will discuss further in the further slides. Okay, so Based upon that, we select based upon what do we need from our system. We want to isolate the vibration or we want to absorb the vibration. We would select that which kind of a technique do I have to apply. Right. After that, what kind of a vibration absorber may be needed, passive or active? With a passive vibration absorber, what happens is that it absorbs the vibration because of its properties, right? Its property like its mass, stiffness, its viscoelastic behavior or damping behavior, like that. But you cannot change it, right? Once you have selected a material and you have applied it, you cannot change it. Right. And it may happen that whatever the vibration absorber technique or the system that we have used, it may happen that in some cases it turns out to be a very good vibration absorber, but in some cases it may not be able to, absorb the vibration that nicely. So it would again depend upon the application, right? If I have that kind of a application wherein I know that only this is going to be the type of vibration that my machine is going to encounter, like if the machine is operating in the same state every time, every day, then I can use the passive vibration absorber. However, if my machine may have different kind of a condition, it may have different kind of operating speed, different kind of a masses which is attached to it, then in that case active vibration absorber is preferred, because in active vibration absorber, the absorber is going to change its properties depending upon the type of vibration we are having. Okay, like for example, if I take an acceleration feedback, depending upon what the acceleration of my vibration is, my system is going to give force to the system as a feedback, right? And then third, effect on vibration reduction of control and damping parameter. Okay, so how the damping parameter and changing the control parameter could lead to effects on the vibration reduction. Okay, so this was the overview. Then we come to the first question. Okay, so the first question says that which of the following is used for vibration reduction? Okay, so firstly, when we talk about vibration reduction, I've already again emphasized on why do we need vibration reduction. Okay, now we will simply talk about that what are the kinds of vibration reduction techniques. Okay, so essentially, when I talk about engineering structure, second. Okay, so now if I talk about the engineering structure, which could be anything, it could be a machine, it could be a building, it could be anything. Okay, so it is going to have vibration, because of which we would require vibration reduction. Okay, as I told you earlier also, in order to reduce the vibration, I have two main options. One is when I isolate the vibration, and the second one is when I absorb the vibration. Okay, so first we'll talk about isolation. Vibration isolation. So firstly, what is vibration isolation? Right. Isolation basically refers to where we prevent the transmission of the vibration to any other part of the system or to the ground or anything. Okay. So what do? We stop the vibration from the transmission. Okay. So in this case, we prevent the vibration Okay, so we essentially prevent the vibration from transmission. Okay, we are not stopping the vibration, mind it, we are not stopping, the system is vibrating. Okay, but what we are doing is we are not trying to stop it. What we are doing is that we are going to isolate it. We are going to apply some okay, I'll just give the example for that matter. If you have seen, usually the machines which have dynamic conditions of working, they usually are mounted on a rubber support. From the ground there is a rubber support, four rubber supports are usually there, and then the machine is mounted on that rubber support. You know what is that rubber support for? It is for isolating the system from the ground, from the base. Okay, that rubber support has the capability of not transmitting the vibration from the particular machine to the ground level. Okay, likewise, if I talk about vibration isolation, it may happen that, for example, if I have a machine A and I have a sensor mounted over here. Let us say that this sensor is there to measure the temperature of the room in which machine A is there, right? Now, if my machine A is encountering vibration, what is going to happen to the sensor? Sensor is also going to have the vibration. Now you see, when I talk about a sensor, sensors are usually very sensitive to the surroundings and the ground conditions. Okay, so usually the sensors, since it is very sensitive and it is also very delicate to handle, we usually do what? When a sensor is mounted on a machine, see, mind it, the sensor is there to measure the temperature. I've already told. The sensor is not there to measure the vibration. If I would have said this, the sensor is there to measure the vibration, the isolation thing will not come over there. Okay. So what will I do? I will use a rubber support. Rubber. Will apply a rubber, and then on the rubber I will mount my sensor. Now what is going to happen? If my machine A is having some kind of vibration, it will not get transmitted to the sensor. So what have I done? I have isolated my machine A from transmission to the sensor. Okay, I hope this is clear. Now the vibration isolation is further divided into two types. One is the base isolation and the second one is the force isolation. As I've told, I've already given the example, but we'll write it. Base isolation and force isolation. The first question is, what is base isolation? As I've told you earlier also, the vibration isolation in which I isolate my system from the base, from the ground, so that the vibration is not transmitted to my base. Okay, that is base isolation. Okay, so in base isolation, avoid the transmission of vibration Okay, I hope this is clear. Now, then we talk about force isolation. So, what is happening in force isolation? In this, what we are doing is we are isolating the component from unwanted forces. Okay, okay. So, till here we talked about vibration isolation, wherein what we were doing, we were actually not stopping the vibration, but we were isolating whatever was vibrating. Okay, so we were either isolating it from the ground, or if some other sensor or any kind of material is you know, present there on the machine that is vibrating, we are isolating the machine so that none of the force is transferred to the particular sensor or anything from the machine A. Now for the vibration reduction, there is another method which is vibration absorption. So we take a new slide, and here we will talk about first what is vibration absorption. So as I told earlier, in the first case we were not stopping the machine from vibrating, but in this case we will try to, you know, add something in my system, some kind of a system in my system, so that the machine itself is not vibrating. Okay, the vibration is actually dissipated in terms of some other form of energy. Okay, so in this vibration energy is dissipated in some usually to damp out the vibration within the system itself. If I talk about a very common example, the most common example is the suspension system of an automobile vehicle. You know, the automobile vehicle, they have suspension system. So what happens in a suspension system is that we have a dashboard. Okay, so there is fluid in it. So what happens is that because of the viscous nature of the fluid, since whenever the vibration comes, it gets transmitted to a spring. The spring tends to oscillate, right? But the spring is now then connected to what? The dashboard, because of which the movement of the spring, the movement of the spring is, you know, counteracted by the viscosity of the fluid, right? And because of that movement and the viscosity of the fluid, the energy is dissipated. The vibration energy that comes in the system because of, you know, going through some kind of a bump or something, the vibration energy that comes in the automobile, it is then damped out. How? By dissipating the energy in the form of heat through the dashboard that is present in the suspension system. Okay, so yeah, this is an example. So now talking about the type of vibration absorption techniques. So there are basically four types of vibration absorption technique. Okay, first one is the passive case. Passive case means that we select a maybe dashboard. If I say let's select a dashboard, let's select a material which is able to, which is, you know, viscoelastic in nature, which is going to dissipate the energy. All right. Okay, first I'll write. We have passive, then we have active, then we have semi-active, and then we have hybrid. Okay. So first talking about the passive vibration absorption technique. Okay, so herein what happens is that we take a kind of material or we take a suspension system, and the suspension system, for example, it is going to have fluid, and the fluid is going to have a specific value of viscosity. Now, if the automobile is going on a road, it may encounter any kind of a bump, it may encounter any kind of variation of the road. The road is not straight and everything. Now, it is not necessary that whatever the irregularities are present on the road, they are of the same amplitude or same type. Right? It would depend upon the kind of a construction. It can have many different amplitude of holes and bumps, or it may have none, right? So in case of passive vibration absorption system, we take a system, we pre-decide this is going to be its viscosity, this is going to be the mass, this is going to be the stiffness, and this is going to be the damping characteristic. Okay. Now, in the passive case, whatever we pre-decide, we know this is the possible vibration that can happen. We pre-decide that okay, this would be the best for us, and then we apply it on the system. We incorporate it in the system itself. Now, when my system is operating, that passive absorber is going to absorb the vibration. Okay. But it may happen that for a certain frequency, the passive absorber will be able to absorb a high amount of energy, but for certain frequency, it may not be able to absorb that amount of energy. That is a problem with the passive case. But if my whatever the working of my system would be, whatever the operating condition would be, if it is known to me and if it is not very much changing with respect to time, it is better to apply passive vibration absorber because though it is not able to work for different kind of a condition that efficiently, but it has a positive point that it does not require any kind of a input continuously, and that is why it is energy efficient, right? Because when we apply a passive absorber, we just apply it. It is not consuming any kind of energy from outward source. Okay, so definitely it is going to help to increase the efficiency. Okay, so we'll write about passive absorber. So it operates on the inherent property of dissipation of the selected, but does not require any input. Okay, this is a passive vibration absorber. But now the question is that okay, it is fine. But what if my system is actually encountering very different kind of a condition with respect to time? Like if I talk about an ATV, all-terrain vehicle, it is supposed to uh, run on the road. It's supposed to run on any kind of a terrain, right? Maybe it can have a very high bump. It may have a very uh, deep kind of a hole or something like that. It can also, you know, we can drive it on the sand kind of a road. Then during rainy season, it can also get driven on the wet condition of the mud, okay, which usually induces slipping in case of a normal vehicle. So now if I talk about an all-terrain vehicle, if I use a passive vibration absorber, will it be a good idea? I don't think so. You know why? Because for a passive absorber, we know that it will only operate depending upon its inherent dissipation, right? It is going to have a damping coefficient C, and that is what is it is going to be for different kind of a condition it is going to encounter. That is not going to change with time. But if my system is having this kind of a behavior like that of an all-terrain vehicle, that every time it is encountering some other type of a problem, Okay, it is encountering some other type of discontinuity of the road, and hence I still want to reduce the vibration that is induced in the vehicle. So the best option for me is the active vibration absorber. Now, in case of active vibration absorber, it actually works on a feedback controller technique, wherein the kind of a vibration that is induced in the system, they take it as a feedback. It feeds into the system, and depending upon that, what kind of a force is required in order to counterbalance, in order to create a destructive interference, it is going to create, or it is going to apply a force, or it is going to give the input to the system. And that way, with every second of time, okay, the input to the system in order to create dissipation is actually changing, and that is why we call it active vibration absorption. Okay, so if I talk about this, it adaptively reduces vibration and the force changes with time through a feedback loop. Now this is clear. Now, if I talk about semi-active, passive is fine, active is fine. The problem with active is what? It requires continuous input. Even if I am giving force, in order to counteract with the vibration that is being produced, how will I give the force? Definitely I have to give some input. If I have to give some input, the energy that I am giving, total energy I am giving to the system, it now increases, right? And that is why it is costlier. Active vibration absorbers are usually used in Aston Martin vehicles. Aston Martin is a very It produces luxurious cars, and they usually use active vibration absorbers in their car for better experience. But then the cars are costly. Why? Because it requires a lot of input, right? And so it's definitely a choice whether we have to use passive or active. If I know that the operating condition is this, and the operating conditions are not much varying with respect to time, passive is the best option. If the condition is varying very tremendously with time, active is the best. And the third option is semi-active, which actually is the combination of a passive plus active vibration absorption. Definitely, it gives a better advantage as compared to active or as passive. Okay, so it is essentially a combination of. Okay, it is a combination. So definitely, when I want the advantage of both active and passive vibration absorption technique, then I'll use the semi-active vibration absorption technique. Now coming on to the fourth one, which is the hybrid one. Now, the concept of hybrid is that if I talk about semi-active, both active and passive are combined together, and then we uh, use the vibration absorption. Like for example, if I use a MR fluid. Now the MR fluid, which is the magnetorheological fluid, for that fluid, if I change the magnetic field, the rheological properties of the fluid changes, because of which its viscosity is going to change. If its viscosity is going to change, the kind of absorption it is going to give will be better, right? But for hybrid, it is different. For hybrid, what we are doing is that all the time the passive absorption is working. But as soon as the machine feels that now the variation is very tremendous and it is very regular with time, it will switch to the active vibration absorption. Okay. Since the passive is going to give us better efficiency, so usually when the machine is operating at a steady state, it will use the passive vibration absorption. But when my system will go to some transition or transient kind of a behavior wherein the condition is changing with respect to time continuously, then it would switch to what? Active vibration absorption. Now there could be a third option as well, where we'll have passive, active, and semi-active, all the three in the system, and then my hybrid or vibration absorption technique will decide on the basis of whatever kind of a vibration. Like we'll divide the vibration on the basis of its amplitude and frequency. Then if we divide it, then the basis of that it is going to choose whether it should use the passive, active, or semi-active vibration absorption technique. So this is switch between different mode of vibration absorption. I hope this is clear. Coming on to the question says that which of the following is used for vibration reduction? Passive vibration absorber, active vibration absorber, vibration oscillator. All the three options are absolutely correct. Coming on to question number 2. It should be okay. For a spring mass system with a neutralizer system, the response amplitude of the main system when forcing with frequency, this will be. Now, first we need to understand what is a neutralizer. So, we talk about tuned vibration absorber, in which what happens is that if I have a spring mass system, I tend to attach another spring and another mass to my system so that it is able to, reduce the vibration of my system. It is like, for example, if I have this, it is of mass m, and then there are two springs. See, this is my system. What is going to happen? The system is going to oscillate, right? For this, the system is going to oscillate. Now let us consider that this F naught sine omega t is not what I desire. This is not a driven spring mass system, but rather this is a spring mass system, is actually a system, and this F naught sine omega t is essentially a vibration that the system is encountering. Now, if I want to reduce the effect of vibration, I use the another spring and I attach another mass, MAKA, okay, which I call as a absorber or a neutralizer. It tries to neutralize the uh, vibration of my main system. Since I've applied it, how it is going to, help me to reduce the vibration. So you see, if I talk about steady state behavior of my system, so in steady state, x of t is going to be what? Let us say some x sine omega t, and x a of t is going to be, this is the steady state vibration of my system. Now, usually this kind of a system is discussed in the books of mechanical vibration, so I will not get into how do we solve it and get whatever. I'll just write the final value of capital X and capital XA. Okay, so capital X comes out to be KA minus MA omega square F naught divided by K plus Ka minus M omega square into Ka minus Ma omega square minus Ka square. And Xa is going to be what? Ka F naught divided by same term K plus Ka minus M omega square Ka minus Ma omega square minus Ka square. So this gives the amplitude of the steady state oscillation. Okay. Now the question is, capital X is what? The amplitude of oscillation on my main system. Capital Xa is what? It is the amplitude of oscillation of my neutralizer. What am I concerned about? I am concerned about my main system, right? Because that is where I want to reduce the effect of vibration. Okay. So yeah. Okay. So this is what it is. What have we done with the system? Earlier, if I talk about the amplitude frequency response of my system, it was something like this. This was omega p, which is under root k by m. Earlier, when I don't consider the neutralizer. Now, since the neutralizer has come, what is going to happen? I'm going to have two peaks, something like this, right? Now I have to reduce, right? So what am I going to do? I'm going to use this equation, this particular equation. This particular equation, however, you can see it from here also what is going to be the answer, but let us just write the other form, which is in terms of omega. You're going to have x k by f naught will be equal to 1 minus omega square by omega a square divided by 1 plus mu omega a by omega p square. Mu is nothing but m of a by m, mass of the absorber by mass of my main system. This is going to be the final equation. So you see what the question says. The question says, for a spring mass system with a neutralizer system, the response amplitude of the main system when forcing frequency with frequency this will be applied. So we have omega as under root Ka by Km, which is nothing but omega is equals to omega A. So you see the numerator, it is simply going to go to 0. And so my x is going to be 0. So here the answer is going to be 0. So you see what happened? I had a spring mass system. I attached another spring mass to it. I changed my system from single degree of freedom to double degree of freedom system, right? It should induce complexity in my system, which it does. But here in this case, you can see that if the parameters are chosen in such a way, then the effect on the main system is what? It is very significant because my main system is subjected to f naught sine omega t. Still, its amplitude of vibration is what? 0. So you realize, if you physically realize this system, what is happening? My system is actually subjected to f sine omega t, but it is not even oscillating. Why? Because my neutralizer neutralizes the effect of vibration. This is very interesting problem. Now this is for a linear system. Mind it, this is for a linear system. When we talk about a non-linear system, the kind of a behavior could be more complex. Okay, coming on to question number 3. The modal frequency. Okay, so the system is, let me draw it with red color. So this is the system. Okay. Now I have to find the modal frequencies. So the question is, what is a modal frequency? Why is it even required? So you remember earlier, I guess in the second or third week's live session, I discussed about how do we find the solution of a two degree of freedom system, or wherein I had two generalized coordinates. How were we finding the solution? What were we doing? Or even, how were we even talking about the stability of the system? So what did we do? We actually, find the eigenvalues and the eigenvectors of the system. Now, along those eigenvector directions, my system is what? It is decoupled. And if my system is decoupled, I can get two separate solutions. And for a two degree of freedom system, if I have two solutions, then any of the other solution could be written as the linear combination of those two solutions. That is the same concept we use for the modal analysis. What do we do here? We try to find the eigenvalues and the eigenvectors for which we are going to get the frequencies, and depending upon those frequencies, what do we get? We get the decoupled equation. From the decoupled equation, we are able to find out the solution. Now it is again useful. Why? Because this particular system can again be used for what? Vibration absorption. It can again be used for what? A vibration absorption. Okay. So first we'll try to find out the equation of motion. So you see for mass 2m, what do I have? I have 2m x1 double dot. Then I have 2k x1. And here do I have? Here I have k x1 minus x2. Correct? If I talk about the mass m, from the force balance method, what have we done? We have made the free body diagram. Now when we balance the force, we are going to get the equation. So the first equation is going to be, this will give me 2m 3 kx1 minus kx2. Okay. Now I can transform it into what? I can transform it to write into matrix form, which will be nothing but m x double dot plus kx is equals to 0, where my x is going to be what? x1 and x2, and hence my m is going to be nothing but twice of m, 0, 0, m, and my stiffness matrix is going to be 3k minus k minus k, k. Okay. Now, again, for the steady state, I can assume my solution as what? Okay. From that, I can take out the second differential as minus of a omega square cos of omega t. If I put these two in the main equation, What will I get? I'll get minus of omega square plus this whole into a, right, the a ray a1 a2 into cos of omega t is equal to what? 0. Correct? Okay. Now, you see cos omega t, we cannot assume it to be 0. A1, A2, we cannot assume it to be 0. So what is the best candidate for being 0? This. From here, we are going to get 3k minus twice of m omega square minus k minus k minus m omega square. Determinant is going to be 0. Right? Now, if I find the determinant, which is 3k, okay? Now, if I arrange it with the decreasing order of the power of omega, I'm going to get this 5mk omega square plus 4k square is equals to 0. No, here should be a minus. Yes. Okay. Now, if I take 2m square, or maybe just m square, if I take it out of my system will be, my system will become twice of omega to the power 4 minus 5 k by m omega square twice of k square by m square is equals to 0. So this is my equation. Now you know for the system, k is known to me and m is known to me. So what is the unknown to me? Omega, correct? And that is what is going to be my eigenvalue, square of the eigenvalue actually, because you see omega here appears with the power 4. So if I consider omega square as omega naught, then I'll get a second order equation. If I consider if omega square, the above equation becomes twice of omega naught square, 5k by m omega plus twice of k square by m square. Now I know what is going to be the root of this equation. Omega naught 1 comma 2 is going to be minus b plus minus under root of b square, which is going to be 25 k square by m square minus 4 into a into c. 4 to the 8, it is a 16 k square by m square divided by twice of a, which is 4. Right? So now if I write it, it is going to be plus minus 25 minus 16 is going to be 9. Okay, so what are we going to have? We'll have omega naught 1 as 5 plus 3, 8, 8k by 4, 2k by m. And second, we are going to have 2k by 4m, so k by twice of. From here, what are we going to get? We're going to get omega 1 as under root 2k by m and omega 2 as under root k by 2m. These are the two modal frequencies. So this was what we were trying to find out. Okay. So now, initially when I was doing this here, I wrote omega p as under root k by m because this system was not there. The absorber was not there. Then I introduced an absorber and I got two frequencies, omega A and omega B. I didn't write the value. Why? Because I don't know what is going to be the value. We cannot say that one is going to be under root k by m and the other one is going to be under root ka by ma. That is not going to happen because now my system is interfering with each other, right? And so these frequencies wherein resonance will occur will depend on the characteristic of both the system, which we were able to see over here. You see, for this system, if I talk about just the first system, which is this, the second system is this. For both of them, omega naught is what? Under root k by m. But if you see my both the modal frequencies, none of them is equal to under root k by m, right? One is under root 2k by m and the other one is k by under root k by 2m. None of them is equal to the individual natural frequencies of both the system, right? So it is important to learn the modal analysis because of this, because now we have what we have done. We have actually transformed my system this to what? This. But by the modal analysis, now I know the values of, okay, sorry. I know the values of these two frequencies. Okay, so that is why the modal analysis is important. Now, coming on to question number 4. For the system discussed in the previous question, which of the following relation between the modal frequencies is correct? Firstly, we'll write omega 1 square was equal to 2k by m. The 2 square was equal to k by 2m. Okay, so first one is the multiplication and the second one is the addition. So we'll first find the multiplication. K square by m square. So the first option is correct. Second is omega 1 square plus omega 2 square, which is going to be 2k by m plus k by 2m, which is going to be 4k plus k by 2m, 5k by 2m. Option C is going to be the correct. I hope this is clear. Now, coming on to question number 5, derive the equation of motion of the given vibration absorber system. Okay, see, for the vibration absorber system, it is very important that you understand that how do we derive the equation of motion. Because if you're not able to derive the equation of motion, you cannot find the relations that is required, right? If you know how to find the equation of motion, it will be beneficial for you, right? So for this system, we'll do it very quickly, not spending much time on it, okay? So you see, this is a piezoelectric stack actuator based hybrid vibration absorber. So why is this piezoelectric over there? Well, this is essentially for giving the, you can say, controlling the system. This is what? This is a active This is an active vibration absorber, right? Not active, actually, it should be semi-active, right? Because what are we doing over here? It's a piezoelectric. So from the concept of piezoelectric, because of the change in the system, it is going to change the stiffness. Definitely Kp is going to change. And so because of that change of the stiffness, you can see that for the main system, M1, I'm going to have the absorber M2, right? Now for the M2, I'm changing the stiffness. If I'm changing the stiffness, what is going to happen? For the passive case, we had a particular set of the inherent properties because of which it was absorbing the vibration, right? But because of that particular set, like we did in the previous problem, what do? We found out that if my frequency of forcing it is equal to under root Ka by Ma, which is the natural frequency of just the absorber, then my system is going to have zero vibration despite of having a forcing function, right? Similarly, if I use a passive absorber, that is it. Like zero is only going to happen if my forcing frequency is equal to the frequency of the individual natural frequency of the absorber, right? But for this case, what is happening? My K value of the absorber is changing because of the piezoelectric stack. K value is changing. So in this case, the user case for my absorber is now increased. Why? Because I can have a variation of values of K. I can have variation of values of omega for my system, for which it can give me fully absorption of the vibration. Right? I hope this is clear. Just a second. Okay. Now we'll try to derive the equation of motion. Again, we'll just apply the force balance method. So we have M1, we have X1, and then we have a force F of t. So here we are going to have inertia M1 X1 double dot. Then we are going to have K1 X1, C1 X1 dot. Apart from that, here also we are going to have one K2 X1 minus X2. Then we'll have C2 X1 dot minus X2 dot. And then we are going to have a force P, which is going to be because of the piezoelectric, right? Coming on to the second mass, which is M2, I have X2, because of which I'm going to encounter inertia M2 X2 double dot. Then we'll have M2 X2 minus X1. Then there is going to be C2 X2 dot minus X1 dot. And then there is going to be a force because of the piezoelectric, right? So this is what it is, right? Now, since we have already done with the force balance, right? What is required? We just have to write the equation and what we are going to get the equation. So for the first mass, if I write, I'm going to get M1 X1 double dot plus K1 X1, C1 X1 dot plus K2 X1 minus X2 plus C2 X1 dot minus X2 dot plus force due to the piezoelectric stack. This will be equal to what? F of t. This is my first equation. And similarly, I'm going to have second equation, which is M2 X2 double dot plus, okay, sorry, I've written M here, it should be K. This is going to be my second equation. Now coming on to how do we write Fp? So Fp, if I consider that we are just taking the proportional controller, then in that case it will be equal to k into x1 minus x2 plus delta naught, where delta naught is nothing but the initial displacement of my piezoelectric stack. Okay, so but what is the going to be the value of k? So if you see the k3 and the kp are in series, right? K3 is constant, but kp is what it is changing depending upon my type of vibration. Depending upon f of t, my kp is going to change. So, right, kp. Okay. Now this is in series. So if you remember, for two spring in series, how do we write k? It is written as 1 by k is equals to 1 by kp plus 1 by k3. This will give me 1 by k is equals to k3 plus kp by k3 kp. So k is going to be k3 kp divided by k3 plus kp. Okay, so my force because of the piezoelectric stack is going to be k3 kp by k3 plus kp into, yes. Okay, I hope this is clear. Coming on to question number 6. No, the question number 6 says that for the primary resonance condition, the value of the optimum frequency ratio and the optimum damping ratio, considering the mass of the primary system as 8 times of the secondary system is. Firstly, while answering this question, we are actually trying to get the answer through the H infinity optimization. There is something which we call as H infinity optimization. From the question, it is clear that there are two masses, there are two springs. There could be two dashpot. Okay, yeah, there is going to be two dashpot. So why is the H infinity optimization needed? See, it was easy for me to, work with a linear system without damping to find out that what should be the frequency ratio or what should be the damping, not the damping actually, frequency ratio. What should be the frequency ratio, which we actually found out for my system to give me, zero vibration. Practically, it is not possible that I get zero vibration. So what do? We try to minimize the vibration amplitude, right? For that, we use optimization technique because you see, optimization is required because there is not a single variable that is affecting my system. There are multiple variables. The frequency ratio is affecting, the damping ratio is affecting, right? And then we have the stiffness, we have mass. So how do we decide what should be the mass, what should be the stiffness, what should be the damping, so that I get the minimum amplitude of vibration? Correct. And that is why what do? We use the optimization technique. So the H infinity optimization technique, if you want, you can refer to the book. It has also been mentioned in the lecture, and if you'll see the assignment problem, there also it is mentioned. This is a paper which is published in the Journal of Applied Mechanics of ASME, American Society of Mechanical Engineers, where in this H infinity optimization is being talked about. So the H infinity optimization is used to minimize the displacement of the primary system. So essentially this is my objective, to reduce the displacement of my primary system. Now see, if I talk about what are the elements of my system, I have mass, I have stiffness, I have a damping ratio, sorry, damping. Okay, it's fine. So we try to introduce the damping ratio. Why? Because we know that the natural frequency is essentially dependent upon both mass and stiffness. And if we find a relation among omega, knowing that there is a relation between m, we can find about the relation between the k's, right? So if you look over here, first thing that is already given in the system is that the mass of the primary system, it takes 8 times of the mass of the secondary system. So mass of the primary system is 8 times the mass of the secondary system. So there is a parameter mu, which is nothing but a mass ratio, which is defined as mass of the secondary system divided by mass of the primary system, m2 by mp. So if I try to find out mu, it is nothing but 1 by, you can write m2 by, so it should be s. The value is of mu is nothing but 1 by 8, right? So now I know the value of mu. Now by the H infinity optimization, I have two equations that I already know because of the literature, which says that firstly, I define the optimal frequency ratio as 1 by 1 plus mu. This is the optimal frequency ratio, 1 by 1 plus mu. You see, it depends on what? It depends on the mass parameter basically, right? Mu. So if I find out this, what is it going to be? It is going to be 1 by 1 plus mu is nothing but 1 by 8, which will give me 8 divided by 9. And this is going to be, just a second, let me calculate. Okay, this is going to be 0.888. This is my optimal frequency ratio. Now, when I say optimal, why optimal? Because it may happen that the frequency ratio does not have a linear or monotonic trend corresponding to the amplitude. Okay, it may have a non-monotonic trend, right? And so also it also depends, the decreased amplitude depends upon not only the frequency ratio, but it also depends upon the damping ratio, and that is why it is important that we find out the optimal value, okay, in order to achieve minimum vibration. So this is the first thing, optimal frequency ratio. And the second is the optimal damping ratio. The optimal damping ratio is defined as 3 mu by the optimal damping ratio. So if I put the value of mu, what am I going to get? 3 by 8 divided by 8 into 1 plus 1 by 8, 9 by 8. So we'll have 3 by 72, correct? And calculate it. It's going to be 0.04167. This is going to be my what? Optimal damping ratio. So if I choose, if the minimum displacement of the primary okay, I hope this is clear and there is no doubt in this. Okay, now coming on to question number 7. Considering the H infinity optimization, which of the following statement is correct regarding the mass ratio mu? Okay, again we'll write the equation first. We had mu, which was the mass ratio. Then we had optimal frequency ratio, which was 1 by 1 plus mu. And then we had the optimal damping ratio, which was under root of 3 mu by this. Now, if I talk about the optimal frequency, okay, so you see, if my mu is equal to 0, if my mu is equal to 0, what is my optimal frequency ratio? 1, which means that there is no secondary system, right? If my mu is 0, it means that the secondary system is actually not present. Okay, so the answer is what? 1. Okay, however, if I now increase the value of mu, what do I see? The optimal frequency ratio decreases. So if a plot is going to be something like this, something like this. So what do I see? I see that my optimal frequency ratio is actually going towards what? It's going towards 0, right? It's decreasing, right? So if it is decreasing, what does it mean? If my optimal frequency ratio is decreasing with the increase of mass, okay, what is happening? Then my system response is showing that how my system or what optimized frequency is required. Now, since it is decreasing, it means that the requirement is less. Similarly, if I talk about the plot of damping optimal with respect to mu, you'll see that it has some increasing trend. It will go on increasing with 0. Okay. So if it is going on increasing, what does it mean? It means that if my mass is increasing, my mass of my secondary system, if it is increasing or the mass ratio is increasing, the amount of damping that is required by me, the amount of damping that is required by me for getting the minimum vibration, okay, minimum vibration, it is increasing. I need more damping in order to get the minimum possible vibration, correct? So what do I get to know? That the mass ratio plays a very important role. Eventually, mass ratio is the one which is from which we are able to decide what? Both the frequency ratio as well as the damping ratio, right? So what do I get to know? that with the increase of the mass ratio, the amplitude at natural frequency have what? Increases or decreases? It decreases. Okay. Now coming on to question number 8. For the system discussed in the previous question, the frequency response is shown below. Which of the following is incorrect? Okay. So the system does not show. Yes.
Hello, ma'am. In the last question, whether the option A is correct or incorrect?
Okay. You see the first, both the options, if you talk about both the options, they are actually different from each other, opposite of each other. So among both, only one can be correct at a particular point of time, isn't it? Hello, am I audible?
हेलो.
Hello?
हाँ मैम, एक बार एक्सप्लेन करेंगे मैम.
दोबारा से?
What you have said, actually, there was a network problem.
Okay, first I'll just complete the question, then I'll discuss it at the end. It'll be fine.
Okay, ma'am. Okay, okay, ma'am.
Okay. Okay. Just a second. Okay. Okay. The system discussed in the previous question. Hmm, which question am I? Okay, not the previous question, it should be this question number 5. Question number 5. Okay. The frequency response is shown below. Which of the following is incorrect? So, the system does not show resonance condition for alpha is equals to 0. Now, you see, firstly, we'll see what are the plots. So the plots is basically the amplitude variation with respect to what? A frequency omega, and it shows that how it is changing with respect to your damping ratio and alpha. Okay. So the question first, so the first option says the system does not show resonance for alpha is equals to 0. It is saying that it does not show resonance for alpha is equals to 0. Well, this option is correct, not correct actually, because it is showing a resonance condition. You can see for alpha is equals to 0, we have peaks over here, right? And we have a very high amount of peak, right? So definitely it is showing. Now, essentially for a non-linear system, resonance does not mean infinite amplitude, right? It is actually a high amplitude. Okay, so the system does not show resonance for alpha is equals to 0 is essentially it is the incorrect option. Okay, so the system response for alpha is equals to 0.3 reduces the resonance effect. Definitely it reduces the resonance effect. It is visible from here that this is the alpha is equals to 0, you see. So here you can see that earlier my response was somewhere over here. Now when I have applied alpha is equals to 0, the response has decreased this and this. Okay, that too for if I take omega 1, this is where I am going to get what? The minimum value of amplitude. Okay, for the minimum value of amplitude. Omega is essentially the frequency ratio, right? So for that, this omega is going to give me the minimum value of amplitude, correct? So if that is the case, then yes, it has reduced. So the system response for alpha is equal to 0 reduces the resonant effect. This is a correct statement, and therefore this is not the correct option, because in question it is asking which of the following is incorrect. Okay, the alpha and the optimum damping ratio is 0.3. The optimum alpha should be optimum. Optimum alpha and the optimum damping ratio is 0.3. Now, if I talk about the optimum values, see for the damping ratio, 0.3, if I see, yes, it is giving me the minimum value. Therefore, it is the optimum condition for me, right? And if I talk about the value of alpha as 0.3, yes, it is giving me the minimum value. Among the three options that has been provided to me, it is giving me the minimum, right? It is giving me the minimum. So the optimum alpha and the optimum damping ratio 0.3 is correct. This is not discorrect. Now, there exist 2 points in the frequency response through which the curve passes irrespective of the tuning ratio. Yes, that is true for this case. You see omega and omega b. No matter whatever the value of the damping ratio is, right, the uh, curve always passes through this point. But the question is for the tuning ratio, which is alpha. For the alpha, this is not the case, right? For the alpha, this is not the case. For the damping ratio, that is true, but for alpha, it is not true. So this is the incorrect option. Okay, I hope this is clear. Now, what I was saying over there, that optimal values, you see, that is why we find out the optimal values, right? Because here you see, increasing the value of the damping parameter or the damping ratio is essentially decreasing what? My amplitude with respect to omega. It is also reducing the resonance effect. You see, these both are my maximum values, which happen to appear at where the resonance values, right? But here also, if you see what is happening, these two values are also reducing. With respect to what? With respect to your omega, right? So that is why we say the optimal values. Now again, if I talk about the parameter alpha, here also you can see with the increase of alpha, the resonance effect is reducing, right? In fact, it is also important to see that for omega 1, I'm having the minimum amplitude that is possible for all the values of omega, right? I hope this is clear. Now coming on to question number 9. Uh, just a second. Yeah. Okay. The following results show the frequency response for two cases of feedback system. Which of the following is correct? Firstly, what is a feedback system? A feedback system refers to a system wherein we use the feedback. System response, we take it, we feed it into the system again so that my response of the system I can control, right? Feedback essentially means that if this is my system, this is the output. I take this output and this is my input. I take this output, feed it into the system so that my input actually depends upon my value of output. All right. This is what the feedback system is. This is my feedback. The output of my system is taken in as a feedback. It is given to the controller and then my input is decided based on what I want as an output. Okay. So feedback controllers are a very important class of controller in case of control systems, And same concept is applied for the two cases which are mentioned over here. The first one is for the acceleration feedback. Second one is for displacement feedback. Okay. First question is what is acceleration feedback? So this is my system. This is the output. Output can have various forms like position, velocity, acceleration. Okay. Now, for example, I know what I want as an output to my system. Okay. I just take the acceleration value. I compare the output I require and the output I'm getting over here. Yeah. Over here, what am I doing? I'm giving it the feedback. And now my input will be decided on the basis of what? On the basis of the difference between what? The desired acceleration and the current acceleration. Okay. So in case of acceleration feedback, the acceleration output is actually taken as a feedback sent towards the input of my system. The controller then decides that what kind of input should be given to the system in order to get the particular kind of a acceleration. Okay. So for the first case, if you see, I have a parameter alpha, okay, which I'm changing. Now you can see for alpha very small, the the amplitude is high. It is of significant value. But as soon as I increase my value of alpha to 0.5, this reduces. The amplitude reduces. How much? Almost 3 times it reduces, right? And now when I take alpha 0.99, you can see how much the amplitude is. 1. Essentially, this is amplitude ratio. And if I talk about amplitude ratio, one means what? Whatever is my input, output is the same. And it is not having any kind of increase in the value of the amplitude. Okay. So this is my effective acceleration feedback with the variation of parameter alpha. Now, when we talk about displacement feedback or the position feedback, what is happening over there? In this case, for the system, if I have an output, I have position, velocity, acceleration. Now what will I do? Take this, send it to the feedback. On the basis of this, my input will be decided. Okay. And now I'll work on the basis of my position. Okay. How my position is changing, and if there's a variation in the position, my input is going to get decided on the basis of how much of the variation is required so as to attain a particular position. Okay, fine. Now, if I talk about the response for the position feedback, look over here. For alpha 0, again, I have a significant amount of amplitude. Here you can see, and it is almost similar or to that of what I got for the lower value of alpha for the acceleration feedback. But For displacement feedback, when I take alpha 0.4 or 0.5, the response is quite same. The variation is now not that much, right? The variation is now not that much. It is still having some good amplitude for the resonance condition, right? So if I have a choice of selecting that which feedback is better, acceleration or displacement, what will I choose? I will choose acceleration. So the option method A of feedback is better than method B is the correct option. The question is, why is acceleration feedback giving me a better result? See, this is a linear system, right? If I talk about a spring mass system, let us just talk about a spring mass system. I have two springs, two masses and everything. And for the primary system, I have to reduce the amplitude, right? For the acceleration feedback, I'm having the response of acceleration. Then I'm comparing it with the acceleration I wanted, right? On the basis of that, we are giving the input. Now, what could be the possible input that I can give to a spring mass system? As per my understanding, force is the best that I can give. Force is the best that I can give. Now, for the acceleration, you see, acceleration is actually the second uh, derivative of position, right? So, uh, the rate of change of position gives the velocity, and the rate of change of velocity gives the acceleration. So, you see, if I'm able to control the acceleration, which is the second derivative of position, definitely my position is going to get controlled. Why? Because I'm actually controlling its second derivative, which is getting integrated twice. Correct. So if at the base, which is the acceleration, if I try to control the acceleration, it is easier for me to control the position because position is obtained from where? From the acceleration itself, right? But when I talk about a position controller, position feedback, I'm actually controlling the position. So my control in, sorry, not control input, actually input is being decided on the basis of what? Is being decided on the basis of the change in the position, right? So, and it is not giving me that good control over my system, right? So that is how you can think. However, this is for a linear system. If we talk about a non-linear system, then it becomes very difficult because for the non-linear system, there are non-linearities that are also there present in the system. And it may happen that my position control can give me a better result, or even the velocity control can give me a better result as compared to the acceleration feedback. But definitely, acceleration has its own advantage because here we try to control the second derivative. And yes, so coming on to the 10th question first. Uh, okay, first we'll discuss the 10th question only. Okay, so here we talk about which of the following is correct regarding the stacked piezoelectric actuator. First, we'll talk about what is a piezoelectric actuator. So essentially, a piezoelectric actuator essentially consists of a piezoelectric material. Now, what is a piezoelectric material? So essentially, a piezoelectric material is a material that shows the actuation or deformation. Actually, no, not that. If we give some kind of a displacement to the piezoelectric material, it is going to develop charge around it. Okay, so what happens is that we have piezoelectric effect. So what happens is a piezoelectric effect. This is my system. And if I try to compress it, it is going to be something like this. If I take a normal material, rubber band or maybe rubber or something like that, and if I try to push it like this, what is going to happen? It is going to come back to its original position. Okay. If I try to take this water bottle and I apply a huge amount of force and I try to push it, what is going to happen? A dent is going to be a dent will occur on the surface, and the dent is going to remain there until and unless I don't try to reverse it back, right? In this case, if I push, it changes the length, but along with that, it also develops some charge. This is known as the piezoelectric effect. Okay, wherein a mechanical deformation of the material induces charge on the surface. Okay, so essentially mechanical deformation or deformation is my input and charge is my output. The piezoelectric actuator also has one more special effect, which is known as the reverse piezoelectric effect. Reverse piezoelectric effect. What happens in this? In this case, if my material is like this, and if I apply charge on it, it is going to result in what? Deformation. So if field is applied on the material, it results in mechanical deformation. So here my charge is the input and deformation is what? My output. Okay. Now that's fine. These are the two principles on which the piezoelectric actuator is going to work. Okay, that's fine. Now they are talking about stacked piezoelectric actuator. What does a stacked piezoelectric actuator mean? So see, if I take a piezoelectric actuator and then I paste another one on it, another one, another one, another one, another one, something like this. Okay, and now if I apply a voltage across it, across every layer I'm applying the voltage. Okay, like here I'm applying some voltage, then here I'm applying some voltage, same voltage, let us say here, here, here. Okay, what is going to happen? Every layer is going to show what? Deformation. Every layer is going to show deformation, right? Now, if my every layer is going to show some deformation, what is going to happen? For example, this layer will have delta 1, delta 2, delta 3, delta 4, delta 5, 1, 2, 3, 4, 5, 6, delta 6. Total delta is going to be what? Sum of the every displacement of every layer. Correct? I hope this is clear. There is no doubt. Because see, what was happening earlier here? We were applying voltage and this was resulting in a deformation. Now we were applying voltage in a on a single layer. Okay, now we take multi-layer of these piezoelectric material, and then we apply voltage on each layer. Then we apply voltage on each layer. Okay, so because of the application of voltage on each layer is going to what? Show deformation. For now, I've assumed that all the six deformations are different. It could be same also if my dimension is same and the voltage I've applied is the same. But what if the thickness is different? Okay, what if the voltage that applies is different in each layer? In that case, the deformation of each layer is going to be different, right? But what is important is to note that the total deformation is going to be what? It is going to be the addition of all the deformations, correct? Because you see, the first layer, it was something like this earlier. It became this. This is delta naught, right? For the first layer. Second layer, let us say was something like this, delta 1. Now these both layer were what? They were together, right? So earlier if it was x1 and this was x2, now this is what? X1 minus delta naught, x2 minus delta 1, right? So from x1 plus x2, now my thickness is what? x1 plus x2 minus delta naught plus delta 1. So my total deformation is what? Delta naught plus delta 1. So it is what? It is additive in nature. And if I talk about the application, why is it required? Because it is preferable that instead of using a very thick stock of my piezoelectric actuator, I take thin layers and then I try to attach those thin layers because then it is easier for me to control it. Because for the thick layer, if I talk about the thick layer, it is going to have much more stiffness. If I take a thick layer and then I try to apply voltage, it is going to have a much more thickness as compared to a thin layers which are stocked together, right? That is why it is preferable that we use. Like for example, I work on dielectric elastomers, and dielectric elastomers are essentially a type of piezoelectric material. Like piezoelectric is essentially a crystal, and dielectric elastomers are elastomers which show only the reverse piezoelectric effect, not the piezoelectric effect, only the reverse piezoelectric effect. So in case of dielectric elastomers, we use the stacking of the dielectric elastomers on one another so that it is beneficial for me to get larger deformation. Since you can see over here that the deformation is what? It is actually adding up. Okay. So for each layer, if I'm getting a small amount of deformation, if I add multiple layers, then what is going to happen? Then I'm going to have multiple times of the deformation. Okay. I hope this is clear. If I talk about the options. It consists of multi-layer of piezoelectric material and is an active system. Okay, this is true. See, I'm not saying that it is an active absorber, but rather I'm saying it is an active system. When I talked about an active absorber, I was talking about a system wherein, with time or depending upon the displacement, my feedback that is given to the system was changing, right? But when I was talking about semi-active vibration absorber, there is where I will consider the piezoelectric actuator or the MR fluids and everything. Okay. But what I'm trying to say over here is that it is an active system. Why am I saying it is an active system? Because see, here, electric field changes its dimension. So my electric field, if it is changing the dimension, what are the probable things that could be able to change? Well, it is going to change the stiffness because it changes the dimension. So in one direction my system is compressed, in the other two direction it is relaxed. So definitely the system is stiffer as compared to the earlier one. Because this kind of a system, it is definitely going to possess a nonlinear kind of a behavior of stiffness. It is not going to have a linear stiffness, right? Because it's a material. Material possesses nonlinear stiffness. So its stiffness is going to change, right? Its dimension is going to change. So we are calling it active because with the variation of the electric field, what is happening? It is changing its dimension. It is what is also happening is that if we are applying some change in, like if I'm taking a piece of electric material and I'm stretching it or compressing it, it is going to develop electric field in the on the upper and lower surfaces, right? Now, because of the appearance of the electric field, what is going to happen? The appearance of electric field is going to cause change in the system behavior, definitely, right? So it is an active system. So the first option is correct. The displacement of each layer is additive, which is true, as we have already seen it, that each layer was showing an additive layer because everyone was giving us some deformation, and that total deformation could be what? It could be added to get the value of the total deformation, as I've seen over here also, that if we consider two layers of x1 and x2, and then one deforms by delta naught, other deforms with delta 1, then the total deformation is what? Delta naught plus delta 1. So the option B is correct. It deforms in the direction of the applied electric field. Yes, this is true. It deforms in the direction of the applied electric field. Wherever the electric field is applied, in that direction only the thickness is going to reduce, and in the other two directions, what is going to happen? There will be change of the dimension in the other two directions, depending upon if the material is incompressible or not. But definitely, in whichever field the electric field is applied, it is going to cause what? It is going to cause the change in dimension in that particular direction. And the fourth is it shows linear behavior. No, it is not going to show a linear behavior. Or else we cannot even say if it is going to show linear behavior or not. I mean, if I consider just a small deformation, very small deformation, then we can say that it is linear because, again, the concept that if I take a circle and if I take a very small part of the circle, it will appear as a straight line to me. It will appear as a straight line to me, right? That is true. Similarly, for the piezoelectric material also, if we consider very small variation of the dimension, then we can say that the behavior is linear. But for large deformations, this statement is not true. Okay, like in case of dielectric elastomer, when we talk about dielectric elastomers, the voltage, so basically there's a layer of elastomer, and then we have electrodes over here. So when we apply positive and negative charge, these two charges tends to compress the material, and so it results in some behavior like this. Okay, you can see that there is a reduction in the thickness and there is an increase in the length, right? So in this case, the behavior is not linear. It is essentially non-linear because the variation, it depends on the second power of the applied voltage. The pressure that is applies, it depends on, it varies with the square of the voltage, and so definitely it is not a linear behavior. But if I consider a very small amount of variation, we can say that the behavior is linear. However, it is essentially non-linear. This dielectric elastomer is also considered for the vibration absorption because these material, as you can see, and changes the dimension, and these are essentially modeled through hyperelastic materials, which happens that you cannot compress it uh, up to a certain, like, up to, you can compress it up to a certain amount only, and you can stretch it up to a certain amount only. Okay, so there is a kind of a well behavior of stiffness, like it's a hardening kind of a material. Like if you keep applying the pressure, if you keep stretching, its stiffness is going to increase, and if you keep pushing it like this, then also its stiffness is going to increase. Okay, so essentially that is why it is used for as a vibration absorber, semi-active vibration absorbers. Because herein, like instead of, like I gave an example of a rubber, like if I have a machine, I would want to isolate its vibration, I would just mount it on for rubber, and then that way it is not going to transmit the vibration to the base. Likewise, I can use electroactive polymers for that case, because in that case we'll have a much wider application, because here I can what? I can change the stiffness of my system. I can change this behaves in a viscoelastic way. So the viscoelasticity also changes with the depending upon the deformation, and hence if the deformation changes, then it is going to show a change in the properties, which could be helpful for me in order to balance out the residual vibration, uh, large amount of residual vibration, large amount of amplitudes and frequency. Okay, I hope this is clear. Now I'll come to the that question that you were asking. You were talking about this question number 7, right?
Yes, ma'am. Now it is clear, ma'am.
Are you sure?
Yes, ma'am. Ma'am, I have a doubt in the last question that
Yes.
you have said that in the piezoelectric material, the when we applied the voltage, the stiffness of the material it changes. Is any effect on the damping of the material?
See, you understand why the stiffness is changing?
Yes, ma'am. Because the
Okay.
length of the system changes, that's why stiffness is changing.
What is changing?
Length or deformation take place.
Yes, exactly. That is changing, and that is why our stiffness is changing. Similarly, if we talk about the damping property, so see, if I consider a piezoelectric crystal, right, there is no point of talking about damping, right? Because a crystal is a solid, and a solid itself, it does not possess some damping. You understand that damping is a property which essentially comes out because of the fluidic nature of a solid. Like, for example, if I take a rubber, or if I take any kind of a elastic material, it is not properly a solid, right? It has the characteristic of a solid, but then it has the characteristic of that of a fluid as well. Because in fluid, if you know, we talk about viscosity, where there are the fluid is divided into multiple layers, and there is a relative slipping between the layer, which causes the dissipation of the energy, right? In case of solid, that happens if I take it, keep it on a surface and then apply a force, friction is going to dissipate the energy. While in case of fluids, there is the, slipping of one layer on the other, which results in the uh, change of the energy. But if I talk about a piezoelectric actuator, you know, if it's a crystal, we cannot talk about the stiffness. If it's a elastomer, okay, now there in market there is piezoelectric elastomers as well, wherein we take very small crystals of piezoelectric material, and then we mend it into the elastomer. Like we usually take the elastomer, we burn it up to a certain temperature, then it converts into the fluid form, then we mix the piezoelectric particles, and then it behaves like a piezoelectric actuator. So if I talk about that elastomer possesses viscoelasticity. Okay, so because of the viscoelasticity, there is, dissipation of the energy. So if I talk about that kind of a piezoelectric elastomer, definitely the change of deformation, like the deformation is definitely going to affect the damping property as well. Okay, I hope this is clear.
Okay, thank you.
Okay, so this is it for today's live session. I hope it was interesting, and we are left with only two live sessions. And also, I guess on 16th, let me just check. Yeah, on 16th, Wednesday, I'll be taking an extra session of 1 hour, wherein we will revise everything, and we'll just then end our live session in the course. We'll be revising everything in one go about what we studied about nonlinear vibration in this whole course. Okay. And for the two left live sessions, it will again happen on Tuesdays only, 6 p.m. to 8 p.m. And since we are in the end of the course, if you people have any doubt, then it is better to just keep it, and we may discuss in the coming three live sessions. That will be very beneficial for everyone. And yeah, okay. For today, that's it. Thank you, and we'll meet again next week, Tuesday.